Good evening, everyone. I welcome aboard to this journey. I welcome you all on the behalf of StudyIQ IAS English. My name is Pritesh Maturkar. I extend my warmest regards to everyone, those who are joining me on this endeavor, those who are joining me on this guided world tour, wherein I, as your able philosopher, mentor, and guide, and of course, a friend, will take you on a different aspects, will take you on a different trajectory, will take you on a different level with regards to understanding the physiography of Earth per se. In short, we'll be appreciating the beauty of this planet, and while we appreciate the beauty of this planet, I will be using the most potent tool for appreciating the beauty, that is maps. So I welcome aboard to those who are watching me for the first time today or those who are continuing this series with me. So today being the 16th lecture and this being a continuing series. So we will pick off from where we left yesterday, and in a short while we will start analyzing the present day status too. So before I move ahead, I quickly like to point out some of the important things for you all as to how we proceed with the things. So this series or this endeavor has been especially started by StudyIQ IAS English for you all to get conceptual clarity of the most daunting phenomenon in geography discipline and in general, that is Atlas. So using Atlas, I want that each and every one of you should have a working understanding of the world physiography, and using Atlas you should be able to answer roughly 50 to 20 marks in prelims and approximately 100 to 200 marks in mains. And if essay comes in your purview or some of the questions of your optionals come in purview, if GS3 comes in purview, then we can easily extend our coverage to around 300 to 400 marks too. So guys, this is my bigger aim with you all, that using Atlas, using the detailed knowledge of these sessions, you should be able to cover roughly 15 to 20 marks in prelims and approximately 200 to 300 marks in mains. So the content which I'll be focusing on primarily in these sessions will be dedicated to having a utilitarian value in the mains and the prelims. I will not diverge from the topics which are not important from the civil services prelims and the mains perspective too. And there I say, I will also inform you with certain topics, with certain developments which will be integral to shaping your character and your personality too. Because whenever you will go for the interview round, your personality should reflect that yes, you have a working understanding of the world. So basically using Atlas, we will be understanding the complete world, and the most important thing, using Atlas, we will try to paint a picture of what is happening in the present day scenario. So even it is my greater endeavor that I am painting current affairs for you all through these sessions so that you understand what is happening today and how it will affect the future events too. So I formally welcome you all to this journey. So as promised, I give you a typical workflow in every lecture. So the typical workflow is like this, that in the beginning I discuss for 5 to 10 minutes the topics, the concepts which we learned in the previous class, and then I elaborate new concepts to you all, and once you are comfortable with the concepts, we try to apply it on the Atlas. And as I promised, every class will begin with a good image of a location which I covered in the previous class. So the image which you are seeing on the board, the beautiful image which you are seeing on the board, this image is basically of the Pamir Mountains. So the Pamir Mountains are at a tri-junction of Afghanistan, you have Kazakhstan, and you have China. So basically if you see this image, so you will see snow-capped mountains, but these mountains are very barren mountains, they don't have trees, indicating that this is a kind of desert topography. Okay, why this is desert topography, why don't you have any trees? For that we will be requiring understanding of geophysics, of geomorphology. So we will venture into that, but you can see the snow-capped peak mountains, you can also see the glaciated lakes, and just appreciate the beauty. Where you have lakes, there you have small grasses, there you have small lichens. So water is vital for growth of life forms, hence the upper mountain tops are covered with snow, they are devoid of life, but where you have shorelines you have grass. So just keep this beautiful image of Pamir Mountains. It is basically Pamir Knot. Why? Because from Pamir Knot you have bifurcation. Remember we did yesterday the Trans-Eurasian Alpine Mountain System. So from Pamir Knot you have bifurcation of that. how it bifurcates and where it goes in India, how it goes into China, how it goes into Tibet, that we will eventually study. So just appreciate the beautiful topography of Pamir Mountains, and as we appreciate it, let's move ahead. Let's start our today's discussion. So yesterday guys, I did introduce you to the breakup of Pangaea. I did introduce you to how you have the breakup of Pangaea into Laurentia and Angara land, and how you have the present day arrangement of the continents. So the breaking up of Pangaea roughly started 185 to 195 million years ago. Okay, India basically separated from the Gondwana land roughly 120 million years ago. During the same time, Austria also separated. Between Africa and South America, you didn't have Atlantic Ocean. They both of these continents were first joined together. So if I take you to east coast of South America and if I take you to west coast of Africa, you will basically see the same rock structure. You will basically see the same details of the structures over there. Even the physical properties and chemical properties of the rocks over there will match. Why? Because both of these continents were first joined together. Okay, so as they broke up, in the middle of Africa you had marine transgression, and hence I told you that there existed an inland sea where you have present day Sahara, and that inland sea supported good marine life forms. And today the dead carcasses of marine life forms are basically responsible for the existence of the Amazon rainforest. Why? Because winds from Sahara will take up the calcium carbonate dust, they will take up the nitrogen, the phosphorus dirt, and they will all deposit it in Amazon. Amazon being a rainforest where it rains incessantly, so it is devoid of minerals. There is a process called as demineralization. So Amazon is existing because of Sahara. That is how so beautifully our planet Earth is interconnected. So as Pangaea broke up, as India collided with Eurasia, you had upliftment of the Tibet. As the upliftment of Tibet is still continuing. Why? Because India is still under thrusting the Eurasian continent. So the height of Tibetan plateau is bound to increase, and as it is the world's highest plateau and its upliftment is still continuing, it is aptly called as the rooftop of the world. So if anyone asks you what is the rooftop of the world, your answer should be the Tibetan plateau. Okay, so after that I discussed the tertiary alpine mountain building phase, where we did discuss the mountain ranges we have uplifted in the same time scale. So I'm quickly revising the locations for you all so that it again gets imbibed in your brain, and then I will move ahead with the discussion of the Earth's interior, which I think is essential for your understanding of the geomorphology and the geophysics. So I'll be opening the map again for you all. So if I'm opening the Earth and if we are showcasing the location of the mountain ranges which we did yesterday, so I will go continent by continent wise. So in North America you have upliftment of the Rockies. So Rockies, they are the tertiary alpine mountain. So you have Rockies in North America. This white part that you see, this is basically the Rockies. You also have the Northwest Pacific mountain complex. So this is the Northwestern Pacific mountain complex. Okay, so this is one of the mountain range of the tertiary alpine system. Second, you have in the South America, you have the Andes and you have the Cordilleras. So if I'm showcasing you the Andes, so the Andes, they start from the south of Ecuador and they extend till the southernmost tip of Chile. So this complete white part, this is called as Andes. So these are Andes mountains, and mind you, Andes are the world's longest mountain system. Okay, no other mountain system in the world is as long as Andes. Okay, and above Andes, this part again which you are seeing white part, these are called as Cordilleras. These are called as Cordilleras. Guys, I'm again reiterating, I am not yet diverging into the detailed aspects of this. I will venture into the detailed maps of each continent. We will study each and every location precisely. This is just an overview so that you get comfortable with the names. Okay. If I paint a good analogy for you all, so just imagine that you are used to eating only in the Indian restaurants, and one day I take you to a Japanese restaurant, and if you see the menu, will you understand the menu? No. So before going to a new restaurant, you should first know which cuisine are you going to prefer. Do you know the ins and outs of that cuisine? So similar thing I'm doing with you all so that you don't get confused with the main menu. Okay, so I am basically acclimatizing you all to the locations so that when I start covering them in detail, you all are able to bear it with me. Okay, so those of you who are watching, I hope that these things are clear to you all, and that you are getting what I'm trying to say. Okay, so let's move ahead. So you have the Cordilleras, you have the Andes. Andes, they are the world's longest mountain range, and also Andes are the second highest mountains in the world after Himalayas. In fact, the tallest peak of Andes is over here. Okay, the tallest peak of Andes is over here. It is called as Mount Aconcagua. It is called as Mount Aconcagua, and Mount Aconcagua is the tallest peak of the world outside the northern hemisphere. So in the northern hemisphere, you do have Himalayas. Himalayas, they are the world's youngest and the highest mountains, but Mount Aconcagua is the tallest peak outside the northern hemisphere. Okay, so let's not discuss that right now. You will end up confusing. After this, the third entry which we discussed was the Trans-Eurasian Alpine Mountain System. Okay, so you have the tertiary alpine mountain building phase, where you have the upliftment of the Rockies of North America, the Andes of South America, and the third phase that you have, the third mountain system that you have in the third phase is called as the Trans-Eurasian Alpine Mountain System. It is called as what, guys? It is called as the Trans-Eurasian Alpine Mountain System. So what do you mean by this? So there exists a continuous mountain system from the shores of the Atlantic to the shores of the Indian Ocean. Okay, dare I say that if you consider the linearity, if you consider the geometry, it may extend up to Pacific too. But for our reference, we should consider that it exists from the shores of the Atlantic till the shores of the Southeast Asia. So which is that continuous mountain system? So I'm first drawing the line on the board which I drew yesterday, and then I will try to paint in the individual mountain ranges again. Okay, so first I will be using a 3D map, and then I will be moving into the discussions using a 2D map. Okay, so if you see the tertiary alpine mountain building phase, in that you have one mountain system which has uplifted from the shores of Europe up to the shores of Southeast Asia. So that is called as the Trans-Eurasian Alpine Mountain System. So it starts from over here, this Spain, you have one in Italy, then you go across Albania, Greece, then you enter into Turkey. In Turkey also you have in the south. From there you come into Iran. You have the Elbrus mountains over here. In Iran you have two mountain ranges like this. From Iran you will have this mountain range extending. Okay, let me just use a smaller scale so that it fits into everything. Okay, yeah, so let me use this scale. So I'm drawing the again. Okay, so it will start from Spain like this. It will go towards Switzerland. It will go towards the borders of southern Germany. It will go towards Albania, Greece. From there it will come to Turkey. In the Turkey it will also venture out into the south. From Turkey it will go into the Elbrus mountains. Okay, from Elbrus it will come into Iran like this. Iran again you will have an offshoot like this, and then it will enter into Afghanistan. You have the Hindu Kush. You have the Pamir mountains. One branch will go into Pakistan as Suleiman and Kirthar. After that it will enter into India. You will have the great Himalayas, and Himalayas then it will go into the Myanmar as Arkanyoma and Peguyoma. So this complete mountain range which you see, this is called as the Trans-Eurasian Alpine Mountain System. This is called as the Trans-Eurasian Alpine mountain system. Okay, alpine mountain system. This complete mountain range which you see. Okay, so now if I'm painting the individual mountain ranges for you, if I move in country by country wise, continent by continent wise, so again I'm doing it on a physical atlas, but again you don't have to worry, we will cover each and every location holistically. For now, just try to imbibe this image in your brain. So now let me use the 2D map so that you get an even good understanding of the mountain ranges. Okay, and let me just zoom in. So we'll move in region by region wise. Okay. Okay, let's begin. So here on the border of Spain and France, you have a mountain range called as Pyrenees. This is called as Pyrenees. Okay, this mountain range which you see, these are called as the Alps. These are called as the Alps. This mountain range which you are seeing, these two mountain ranges, these are called as Carpathian mountains. Carpathian mountains, and you have the Transylvanian Alps. Transylvanian Alps. So I told you yesterday, Transylvanian Alps are the birthplace of all the vampire stories. So if any one of you has seen the Conjuring universe, in that you have a movie called as Nun. So the castle which is shown is basically this region of Romania. So if anybody wishes to meet vampire, you are free to end up in this region. But please do it after you become civil servant. Till then, you have to focus on the lectures. Okay, jokes aside, then in Italy, you have a central mountain range. This is called as Apennines. This is called as Apennines. Okay, then along Greece and along the Albanian coast, you have two mountain ranges. These mountain ranges, they are called as Pindus mountains. They are called as Pindus mountains, and you have Dinaric Alps. You have Dinaric Alps. Okay, then you come to Turkey. On the northern coast of Turkey, you have a mountain range called as Pointek. You have a mountain range called as Pointek. On the southern end, you have a mountain range called as Taurus Mountains. You have a mountain range called as Taurus Mountains. So recently you did have earthquake in Turkey. So the most devastating earthquake of Turkey recorded in this century. So it happened over here. There is a city called as Gaziantep. There are two active fault lines in Turkey. So that fault lines became active, indicating that this region is not at all tectonically stable. So we'll try to cover such kind of current affairs also. Okay. After that, in Iran, you have two mountain ranges. So you have one mountain range over here, another mountain range over here. Sorry, this is not Iran. Okay. You have one mountain range over here and another mountain range over here. And this part you are seeing, this is called as the Caucasus mountain range. This is called as the Caucasus mountain range. This is called as Caucasus. In Iran, you have Elbrus and you have Zagros. So this is Zagros. This is Elbrus. Okay. I'm first of all painting you for you all on physical map directly, so that when we will do the country by country map, the physical map of the individual locations, you will be already knowing all these entries. So it will be a quick revision for you. Okay. Then you come to Afghanistan and you come to Pakistan. So Afghanistan and Pakistan, this is where you have the Pamirs and you have the Hindu Kush mountains. And then in India, you have this complete range. We call it as Himalaya. We call it as Himalaya. And then in Myanmar, you have two mountain ranges. They are called as the Yomas, Arkan Yoma and Pegu Yoma. So you have the two mountain ranges in Myanmar. You have the Arkan Yoma and you have the Pegu Yoma. So one complete mountain range from the Mediterranean coast, from the Atlantic coast up till the southeast of Asia. So this complete mountain system, this complete mountain belt, it is called as the Trans-Eurasian Alpine Mountain System. And please remember this, guys, that all of these mountains have uplifted in the same time scale. They have uplifted in the same phase. Hence, they are grouped into the tertiary alpine mountain building phase. Prior to this, we did do two mountain building phases. We did the Caledonian mountain building phase and we did the Hercynian mountain building phase. So this is the third mountain building phase which you have. Okay. So now let's move ahead now. Now let us take our discussion ahead with regards to the interiors of Earth. We will discuss those topics which I feel are important from the mapping perspective, which I feel are important from the atlas marking perspective. Okay, so we'll not going into the details of every damn location or every damn kind of entry in geomorphology, not every theory, but the theories which I feel are important for your understanding of the atlas. Okay, so let's move ahead. So now let us study something with regards to the interiors of Earth. Okay, so all of you know that the origin of Earth is basically attributed to the nebular accretion process, wherein the interiors of Earth are stratified on the basis of density. The innermost layer will have the highest density, and as you come out of it, the density will decrease. So the innermost core of the Earth will have the highest density, and as you move out, the density will slowly start to decrease, and the lightest of gases you will have in the atmosphere. But mind you, this was not how basically Earth originated. When Earth originated, it was basically a condensing hot nebula. It was a giant amorphous cloud of gases like hydrogen and helium which started fusing, which started swirling. You had the process of accretion begin. But today also Earth is still condensing. Today also Earth is still cooling. Earth has a living core. You have an outer core which is spinning around a solid inner core. So my endeavor with you all from today onwards will be understanding the somewhat interiors of the Earth, what is causing this to happen and how it is linked to plate tectonics, because our understanding of maps is very essential with regards to understanding the plates of the Earth, like which plates you have on Earth, what do you mean by continental plate, what do you mean by oceanic plate, what do you mean by continental crust, what do you mean by oceanic crust. So all of that we will try to paint a picture from today onwards. So just bear with me. Those of you who are watching me, you are free to comment. Those of you who will watch in a later date, again you also are free to comment. Okay, so let's begin. So if I consider the interiors of Earth now, okay, the interiors of Earth, okay. So interiors of Earth are not a singular layer. The interiors of Earth are basically stratified on the basis of density, stratified on the basis of density, are stratified on the basis of density. They are stratified on the basis of density. Highest density you will have of core. So the core of Earth will have the highest density. Okay, the density of core will be something between 13 to 13.7, and mind you, this is specific density, hence it will not have any unit, whereas the lightest of density will be in the crust. Okay, so on an average the crust will have density varying between 2 to 3.5. Now crust of Earth, you have two distinct layers. You have the division of Earth's crust into two parts. You either have the continental crust where you are all sitting today, where I am standing today. So it's the land surface of Earth, the continents which we saw while the Pangea break apart, and you have the present day arrangement of the continents. So the crust is bifurcated into the continental crust and the oceanic crust. Okay, and the oceanic crust. In between the crust and the core, you have another layer called as mantle. Okay, I'm deliberately not discussing this layer now because for that I will be reading some knowledge of the minerals, so we'll venture into that too. And mind you, mantle will account for roughly 60% of Earth's volume and 80% of Earth's weight. Okay, if I'm considering the mantle, so mantle as a whole will account for roughly 60% of Earth's volume and roughly 80% of the Earth's weight. Okay, Abhay, you are asking why other nebula won't have. Abhay, like for nebulas to have atmosphere, for you need to have a condition called as the Goldilocks zone. Okay, what do you mean by Goldilocks zone? So there is a question that why don't other can't we have planets like Earth outside the solar system? Why can't we have a planet like Earth in other parts of the universe? So the answer to this is that you need to have preferred conditions for formation of planet like Earth, and that condition is called as Goldilocks zone. What do you mean by Goldilocks zone? That Earth is neither so close to its primary star. For us, the primary star is the sun, so we are neither that close and we are neither that far from the sun. Okay, so whatever you have on Earth is basically the sun's gravity, the moon's gravity does impact on Earth. So the condensing of the Earth, the cooling off of Earth was closely linked with the gravitational pull of the sun. So if we were very close to the sun, then the Earth's volume, the Earth's spherical shape would have shrunk like Mercury, like Venus, but we are not that close, so we are somewhat far. So the amount of light which we get, the amount of gravitational pull that we get was perfect for formation of a planet like Earth. Just compare Earth with Mars. Mars is little bit far away from the sun. See where Mars is and where Earth is. So your answer for this, that why can't other nebulas have atmosphere like Earth? First of all, no nebula will have atmosphere. Nebula is just a giant hot cloud of gas. Nebula has to condense. It has to condense to form a planet. It has to condense to form a rocky structure. And as of now, in solar system, rocky structure is existing only on the 4 terrestrial planets: Mercury, Venus, you have Earth and Mars. So your answer is we are in the perfect Goldilocks zone. Up till now, we have only discovered 2 planets which do exist in the Goldilocks zone, but on that planets too, we have not yet discovered atmosphere. Why? Because they are very close to their primary star. Okay. So in between core and crust, you have mantle. So you need to remember that mantle will account for roughly 60% of the Earth's volume and 80% of Earth's weight. But for understanding mantle, we do need understanding of the minerals of Earth, the mineral composition. So we will come it at a later date. So you have the continental crust and you have the oceanic crust. The continental crust will have density between 2 to 2.5. The oceanic crust will have density between 3 to 3.5. And mind you, only 25% of the Earth's crust is continental crust. Let's 75% of the Earth's crust is oceanic. So if I'm asking you, how is Earth? If some alien is seeing from outside the solar system, imagine I am an alien. Okay, I have now come from a distant galaxy, and now I'm trying to see the Earth for the first time. So what is the color that I will see? I will see Earth as a pale blue dot. Why I will see Earth as a pale blue dot? Because 75% of the Earth's surface is covered by oceans, and below the oceans you will have oceanic crust. So the common answer that why the crust of the oceans is having more density, because it is little bit in the depths. You have the water existing, the pressure on it, and also when this crust is forming at a depth. So in general, the density will increase with depth. So this is the main distinction between the continental crust and the oceanic crust. Now, before I move ahead, before we need to understand that how do continental crust and oceanic crust drift and what is their interaction, first we need to understand the mineral composition of Earth and little bit idea with regards to the rocks of Earth. So in the interiors of Earth, now we should start discussing the mineral composition and the rocks of the Earth's interior and the exterior too. Okay. So now guys, I'm taking you on a journey where I will be discussing some of the minerals, some of the rocks. I won't be venturing into the depths of it, but only those entries which I feel are important from mapping perspective. And dare I say guys, please listen to me very carefully. Dare I say, these entries are roughly 50% of the entries which you have to do in your mains curriculum. So relax, chill. I am here, Pritesh is here, so I am already covering 50% of your main syllabus in this curriculum only. Okay, so just chill, relax, focus on me, ask me if you have any difficulty, and grasp the knowledge, move ahead. Okay, so let's assume, or let's bifurcate the earth as a whole, and let's bifurcate the earth only as the crust. Why? Because you and me, we are all primarily interacting with the earth's outside environment on the crust. We have got nothing to do with the earth's core. Are you interacting with the earth's core on a daily basis? Of course not. Is the lava and magma coming in your location every day? Of course not. You won't be living then. Okay, so our interaction with the earth's ecosystem is primarily on the earth's crust. So we will use our knowledge of the mineral composition. We will try to understand the mineral composition of earth using two formats. First, we will try to paint the picture of a planet as a whole. Like if we consider the planet as a whole, so which elements do we have in majority, which elements dominate the earth as a whole, and if we are considering the earth's crust, which element dominate the earth's crust. So after elements we will move into the minerals part, after minerals we will move into the rocks part. Okay, so if I'm considering the earth as a whole, if I consider earth as a whole, okay, if I consider the earth as a whole planet, okay, so can anyone tell me which element you will have in most abundance? Okay, those of you are watching me now, okay, you are free to comment that if I consider earth as a whole, so which element will I have in the most abundance? Okay, the answer is in your blood. Okay, the mineral or the element in your blood which is actually carrying the oxygen. Okay, so the answer is iron, Fe. Okay, if you consider earth as a whole, so the most dominant element, the most dominant element in terms of abundance is going to be iron. In fact, majority of the earth's core is made up of iron. It is made up of solid iron and nickel, and in that iron will dominate. And hence, if anybody asks you that which is the most dominant element of earth as a whole, your answer should be iron. And the second most dominating element is elemental O2, oxygen. So this is when I am considering the earth as a whole. But if I consider the earth's crust only, so if I consider the earth as its crust only, okay, if I consider the earth as its crust only, now the things change. Okay, predominantly you will find iron increasingly in the interiors of earth. As you come out of the interiors of the earth, the concentration of iron will decrease, the abundance of iron will decrease. If you consider the earth's crust only, if I'm painting you the picture of earth's crust, so the most dominating element will be elemental O2, and you will have silica. So if I pick up the soil, if I pick up the land, or if I start digging into the earth's crust, so predominantly I will find elemental O2 and silica. And as you have predominance of silica and O2, so if we want to study the minerals, if we want to study the interaction of the elements, if we want to study the minerals, so predominantly which minerals you need to study? You need to study the silicate minerals, basically the SiO2 complex. Why? Because on the earth's crust you are predominantly finding silica and oxygen. So if we want to study how is the earth stratified, or how is the earth's crust, or how do we have the interaction between the continental plate and the oceanic plate, so your one-stop destination will be analyzing the silicate minerals. Okay, there are different mineral groups, guys. So minerals, if I consider some of the properties of minerals, so the minerals will have their own distinct properties. They will retain their physical and chemical properties. Okay, there will be almost no crystalline, there will be no crystal face to them, and most importantly you will have different mineral groups. So if I'm considering the different mineral groups, if I'm painting the different mineral groups for you all, so the dominating mineral groups are of course the silicates, which we have to study in detail. Okay, you have the dominating mineral group like halides. So if I consider the silicates, so the most common example of silicates, it's quartz. Okay, if you are wearing watches, so the watch is made up of quartz. If I'm considering halides, the most common halide which you find, which you eat daily in your food, which gives taste to your food, and which is the most common salt of the ocean, it is called as sodium chloride. So it is called as sodium chloride, NaCl. Okay, you also have sulfides. Okay, sulfides. Okay, you have sulfides like gypsum. Okay, these are some of the mineral groups on earth. Okay, mineral groups. Okay, if I'm considering another example of mineral groups, so you can even go for oxides. The most common oxides that you have is hematite. Okay, Fe2O3. Okay, iron, hematite, Fe2O3. Okay, and you also have one common group of minerals, carbonates. Okay, so the thing which makes your water hard, you have calcium carbonate and you have calcium bicarbonate. So calcite, calcite, the thing which makes your water hard. So if you are drinking water which is hard, if you are using a hard water for bathing, it will not lather up. So you will have to soften the water. So you will have to do the reverse osmosis to make the carbonates dissolve. So these are some of the dominant mineral groups that exist on earth. Okay, you also have uh, sulfates. Sorry, my bad, gypsum is not sulfide, gypsum is sulfate. Okay, I'm correcting this. Please make sure that you are correcting this too. Gypsum is a form of sulfate. Okay, it's not a form of sulfide. Okay, sulfate is the example of gypsum. Sulfide is where you have the sulfur. So example of sulfide you can get as PBS, plumbum sulfide. It is called as galena. It is called as galena. So these are some of the dominant mineral groups on earth. You have silicates, you have halides, you have sulfates, you have oxides, you have carbonates, and you have sulfides. Out of this, we have to primarily focus on the silicates. Why, guys? Because if we are considering the earth as the crust from only, why? Because your and my interaction will be predominantly with the earth's crust. This layer is the most significant layer with our understanding of the earth. So if we are considering the earth's crust, the maximum concentration is of O2 and silica, and hence it becomes imperative that we only assess, that we only get into the details of the silicate minerals. And there are 3-4 silicate minerals which are very important for our understanding of earth. So I will be predominantly focusing on that 3-4 silicate minerals only. Rest of the minerals will be covered in your later discussions when you will have the advanced level discussions of geomorphology. But for now, just remember 2 or 3 silicate minerals. Okay, so let us begin our discussion of the silicate minerals. Okay. Silicate minerals. Okay, so if I consider the silicate minerals, the most common silicate minerals that you will find, it is called as quartz. Okay, second you will find feldspar. This feldspar is basically alkali feldspar. This is basically alkali feldspar. Another very important mineral, it is called as muscovite, muscovite or mica. Okay, and another important mineral which you need to remember from the silicate minerals perspective are, it is called as pyroxene, pyroxene, and the last you need to remember, it is called as olivine. It is called as olivine. So these are some of the dominant mineral groups of the silicate family. In NCERTs, if you open up NCERTs, you will find 7 or 8 more examples. You don't need to remember those examples. The only examples which I'm discussing on the board, these are sufficient for your understanding of the earth. See guys, those of you who are listening to me live, please get this point, that in civil services examination, you have to laser focus on that information which is having actual utility in the examination. You don't have to cringe in as much information as possible. What are you going to get ultimately? Ultimately, whatever you are studying, it should translate into marks. So it should be in your best interest that you only study those phenomenon which are important from the mains and the prelims perspective. So you just remember this 3 to 5 entries for with regards to the silicate minerals. Rest of it will be done. Okay. So now if I go into the details of this, so silicate minerals will have certain properties. What are these properties? That with increasing depth, if the depth increases, so the density of the silicate minerals, it is bound to increase. So density increases. Okay. Their reactivity increases. They become highly reactive. Okay. They become highly reactive. Their reactivity will increase. Okay. Their color will become dark. So color will become dark. Okay. So the darkness will also increase with depth. Okay. But their hardness will decrease. Please keep this in mind. Their hardness will decrease. So if I'm considering the silicate minerals, their hardness will decrease. So with increasing depth, the density of this mineral is bound to increase. So if I'm going with depth, so in the depths, you will find more olivine, you won't find quartzite in the depth. So if you move from quartzite to olivine, the density is bound to increase. The reactivity from quartz to olivine is bound to increase. The darkness from quartz to olivine, it is bound to increase, whereas the hardness is bound to decrease. So with abundance, the picture which I am painting in front of you, this is with increasing depth, you will transition from quartz to olivine. So the uppermost layers of the crust will dominantly have quartz, but as you move down towards the interiors of the earth's crust, you will predominantly find olivine. So this is the sequence of abundance with depth. So the picture which I have painted in front of you, this is basically the sequence of abundance with depth. The sequence of abundance with depth. The sequence of abundance with depth. So you just need to remember that the uppermost layers will have quartz, and as you move down, you will transition from quartz to olivine. Okay. So again, I am reiterating, if I am considering the properties of the silicate minerals, so quartz will have the least of the density, whereas olivine will have the highest of density, but it will also have the highest of reactivity. It will have the darkest of colors, but its hardness will decrease. Means what? That it will become extremely brittle. Why? Because as you are moving down with depth, as the depth is increasing, what is happening? Pressure and temperature, both of them are building. So as pressure and temperature, both of them are building, the reactivity is bound to increase and the brittleness or the hardness is bound to decrease. So it is just like that. If you start crushing olivine, it will crush like anything. And hence, as olivine is brittle, as olivine is having not that high amount of hardness, so as you move down from the uppermost layers of the crust to the lowermost layers, you have a semi-molten nature of the earth's crust as you move down. And hence, this semi-molten nature of the earth's crust, this is referred to as asthenosphere. And the uppermost layer of the earth's crust, it is called as lithosphere. Because of the dominance of the olivine mineral, the asthenosphere acts as if it is semi-molten, whereas the lithosphere is hard, it is solid, whereas the underlying asthenosphere, it is little bit less brittle, it is rather in a semi-molten state. So what is happening, guys? The lithosphere is actually floating and the asthenosphere. So hence we see the breakup of continents. Like somebody did ask me, I guess it was Abhay only, that why this breakup is happening and how are the continents drifting. The continents are basically drifting because in the lowermost layers of the earth crust you have olivine. Lower means the layer just below the lithosphere, you are having olivine mineral, and this olivine mineral will lose rigidity when it is sustained to stress, when it is sustained to high temperature. As it loses rigidity, so the lower layer of the earth's crust is in a semi-molten state, above which the upper layers can float, they can drift. Hence you have the theory of continental drift, and hence today you are seeing that the continents are drifting. Okay, so if I'm painting a picture for you all, if I'm again reiterating whatever I'm saying, okay, so please get this very, very properly. So if I consider the earth as a crust only, if I'm considering the earth as its crust, so predominantly you have which elements? You have O2 and you have silica. So it becomes imperative for us to study the silicate minerals. It becomes imperative for us to study the silicate minerals. And when we study the silicate minerals, you need to understand 5 to 6 examples. The first example of silicate minerals, we all need to understand it's quartz or quartzite. Then you need to remember, after quartz, you need to remember feldspar. Okay, feldspar, mind you, this is alkali feldspar. This is alkali feldspar. After this, you need to remember muscovite. Muscovite, it is also called as mica. After that, you need to remember a mineral group called as pyroxene. And lastly, you need to remember a mineral group called as olivine. Okay. So if I consider this, so if I'm painting this arrow, so this is the sequence of abundance with depth. So their abundance will increase. Their abundance will increase with depth. Their abundance will increase with depth. Their density will increase with depth. Their density will increase with depth. Okay, their darkness will again increase with depth. Okay, then their hardness will decrease. Why their hardness will decrease? Because as we move down, the temperature and the pressure both are increasing underneath the earth's interior. Hence the hardness will decrease, and the most importantly, their reactivity will increase. Their reactivity will increase. So as we go into the interiors of the earth's crust, olivine loses rigidity. Olivine loses rigidity due to sustained stress. Due to sustained stress. And as it loses rigidity, the lower layers of the earth's crust, which is referred to as asthenosphere. Okay, I will teach you what do you mean by asthenosphere. So the lowermost layer of the earth's crust, not the lowermost layer, but the layer just below at a depth of around 100 kilometers. From 100 kilometers to 300 to 400 kilometers, it is called as asthenosphere. So the asthenosphere will lose rigidity. So the asthenosphere will be rather semi-molten. As it is semi-molten, so above it, the lithosphere will float. Above it, the lithosphere will float or will drift. And hence the answer that why do continents drift? because of which dominant mineral in the earth's interior, rather in the lower layers of the earth's crust, or dare I say the asthenosphere? Olivine. Okay, so you need to remember only this from the interiors of earth's perspective with regards to the silicate minerals. So I will be taking your leave now. Tomorrow we'll move into the discussion of rocks per se. We'll be discussing the igneous rocks, we'll be discussing the sedimentary rocks, we'll be discussing the metamorphic rocks, and some of the some of the detailed discussions of igneous rocks too. And then tomorrow I will teach you what do you mean by shield regions, what do you mean by cratons of the world, and tomorrow we will paint a picture of those regions of the world where you have predominance of minerals. And mind you guys, minerals are very important for today. Why? We are moving towards greening of economy. We are moving towards electric vehicles. And in electric vehicles, you require lithium batteries, you require cobalt, you require manganese, and but naturally, whatever screens you are seeing me on, your smartphones, your laptops, they require copper, they require gold for PCB connectors. So tomorrow you will finally get the answer that which are the most mineral rich regions of the world. So a very important part of your GS paper 3 and also GS paper 1, where we need to understand the geospatial distribution of the resources and its effect on the industries. So tomorrow you will get the answer of that. So tomorrow's class will become very important. Till then, please revise this information which I have given you today with regards to the silicate minerals. Okay, I hope that this was extremely clear to you all, and I hope that you have gotten the concept properly. See guys, it might happen that in some lectures I will not be using the atlas holistically. Why? Because I need to divulge out some information. So please bear with me, because all of this information is extremely necessary for you understanding the movement of the continental plates, for you understanding that why did you have earthquake in Turkey, and such kind of news are very important from prelims as well as mains perspective. So before closing it off, I will quickly like to point out my name. My name is Pritesh Maturkar. Okay, all of the information which I'm divulging out, the relevant current affairs, you can reach out to me on a Telegram channel by joining Geography by Pritesh Maturkar. For joining this, you can just do a global search on Telegram at Geography by Pritesh. So it is in my best interest, and it is also in your best interest that you join this channel. Okay, thank you, Abhay. So everyone, see you all tomorrow sharp at 5 p.m. Till then, please take care, please study hard and smart.